Welcome to this explainer. If you've ever really looked under the hood of a large language model, you've probably stumbled across this exact line of code. Scores equals Q at K dot transpose -2, -1 divided by math dot square root of dk. Now I know, at first glance, it looks like an incredibly intimidating string of linear algebra, but I promise you, by the time we wrap up today, you are going to precisely understand every single component of this transformer attention equation. You won't just vaguely know what it does, you'll know exactly what it computes down to the silicon, why we divide it, and what spectacularly breaks if you just remove that division. So let's dive right in.
Okay, before we touch any math at all, we really need to start with the core engineering problem. Just imagine you're building a search engine. A user types in "best Italian restaurant near me." You've got this massive database of 1 million restaurants, and they're all stored as vectors. Now, these vectors represent meaning, right? So similar restaurants live close to each other in this high-dimensional space, and completely different ones are far apart. The real question is, given your search query vector, how do you mathematically find the most relevant restaurant vector? We basically need a reliable tool to measure how much two vectors are, saying the same thing. To do that, let's quickly establish our baseline. A vector is just an ordered list of numbers. But geometrically, it represents a point or a direction in high-dimensional space. Think about a scalar, like the number 3.7. It carries magnitude but zero direction. A vector, on the other hand, carries both magnitude and direction. And this is an absolutely vital prerequisite, because the operation we're about to explore, the dot product, takes two vectors, operates on them, and spits out a single scalar. Bottom line, if we don't have vectors, we literally have nothing to operate on.
So here is our roadmap for today. 1. The alignment problem. 2. Visualizing the math. 3. Computation and code. 4. Powering modern AI systems. 5. Failure modes and limits. And finally, 6. The permanent mental model. Let's get going.
Section 1, the alignment problem. Let's build up some geometric intuition first.
Picture two arrows drawn from the exact same origin point on a piece of paper. In case 1, both of these arrows are pointing in the exact same direction. If I ask you, hey, how much does arrow A agree with arrow B, the answer is completely. It's maximum agreement. But now look at case 2. The arrows are perpendicular, exactly 90 degrees apart. One points to the right, the other points straight up. If you shine a light from one arrow onto the other, it casts zero shadow. They share absolutely zero agreement. And this brilliantly illustrates exactly what the dot product captures: how much of vector B lies in the exact same direction as vector A.
Section 2. Visualizing the math. Now that we have that intuitive foundation, let's decode the actual mathematical symbols. Notice the two identical ways we can define the dot product here, and we're going to skip the textbook hand-waving. On the algebraic side, which, by the way, is what our computers actually use, we multiply the corresponding components of our vectors together, ui times vi, and then sum them all up across every dimension. On the geometric side, which is how we as humans intuitively understand it, we multiply the length, or the L2 norm of vector u, by the length of vector v, and then multiply that whole thing by the cosine of the angle between them. Magnitude times directional agreement. Both formulas prove the exact same thing, a single scalar representing agreement.
Let's walk through a super concrete numerical example to really cement this. Imagine vector u is 1, 2, 3, and vector v is 4, 0, -1. Step 1, we multiply term by term. 1 times 4 is 4, 2 times 0 is 0, 3 times -1 is -3. Step 2, sum them up. 4 plus 0 minus 3 equals 1. So our dot product is exactly 1. Now both of these vectors have a length of roughly 4, but their dot product is tiny. Why is that? Well, if we use our geometric formula to verify the angle, we find the angle between them is 86.3 degrees. They are almost completely perpendicular, meaning they share barely any direction at all. It's kind of amazing. The math perfectly distills their entire relationship down into a single number.
Section 3, computation and code. The theory is elegant for sure, but as engineers, we have to ask what the hardware is actually doing.
When a computer calculates a dot product, the processor loads two floating point numbers from memory, multiplies them, and adds the result to a running accumulator. It just repeats this over and over for every dimension. The crucial point to remember here is that this operation scales linearly, or O of n. But here is exactly why modern GPUs absolutely love this. They have dedicated hardware called fused multiply-add, or FMA units. They can execute that entire multiplication and addition step in one single clock cycle.
For a piece of silicon, the dot product is pure arithmetic with perfect predictable memory access patterns. If you try to write this from scratch in pure Python using a for loop, it's going to be incredibly slow. If you step up to NumPy, well, now it uses CPU-optimized routines with SIMD instructions to process multiple elements per clock cycle. Suddenly, you're 10 to 100 times faster. We also typically stick to float 32 precision here to save on memory. But in modern deep learning, we're using PyTorch. PyTorch runs highly parallel, batched matrix multiplications directly on those GPU FMA units we just talked about. And remember, a matrix multiplication is really just thousands of dot products organized into a massive grid.
Section 4. Powering modern AI systems. Let's zoom back out and connect the dots.
We are definitely not going to use vague statements like, "it's used in neural networks." Let's map out exactly where the dot product acts as the core engine. In a standard linear layer, it calculates how much an input matches a neuron's stored weight pattern. In a model like CLIP, it matches the alignment of an image vector against a text vector. In dense RAG retrieval, it scores your search query against the target document. Everywhere you look, whether you're finding relevance, measuring similarity, or triggering a neuron, it is quite literally just a dot product.
And this brings us right back to its most famous application, transformer self-attention. Just look at this step-by-step dissection. We project our inputs into query, key, and value matrices. Then we compute the attention scores. Now, what exactly is Q@K.T? It is an all-pairs dot product. It asks the network, how much does this specific query token agree with this key token? We scale it, run a softmax to turn those scores into probabilities, and then compute a weighted sum of the values, which, surprise, surprise, is yet another dot product. If you remove the dot product, transformers literally cease to exist.
Section 5. Failure modes and limits. Because things do break, and you need to know why. 22.7. I want you to keep this number locked in your head. If you take two completely random vectors with 512 dimensions and compute their dot product, the standard deviation of that result is 22.7. The variance grows linearly with the dimension of the vectors. And let me tell you, 22.7 is not a small number when you're dealing with machine learning. If you leave this unchecked, these massive magnitudes will completely break a neural network.
And here is the massive aha moment I promised you. Why do we divide our attention scores by the square root of the dimension size? Well, if we don't scale it, that massive variance feeds straight into the softmax function. When softmax sees really large numbers, it saturates. It outputs a near one-hot vector, basically giving almost 100% of the attention to a single token. And when softmax saturates, your gradients vanish. The model just stops learning completely. By dividing by the square root of dk, we normalize that variance right back down to 1. We literally rescue the gradients and keep the whole model learning. It's a lifesaver.
Now, here are a few other really common engineering bugs to watch out for. If you're building a retrieval system and you forget to L2 normalize your vectors, a completely irrelevant document that just happens to have a massive vector magnitude can entirely overpower a highly relevant document with a smaller magnitude. You'll get completely wrong similarity scores. You also have to watch out for confusing a simple 1D dot product with batched matrix multiplications, memory layout issues when you're transposing tensors, and float 16 precision overflow, which will happen if your values exceed 65,504.
Section 6. The permanent mental model. Let's wrap this up with the cutting edge. We know standard attention requires massive memory because computing every single dot product pair creates a huge quadratic bottleneck. But look at the research frontier right now. Flash attention solves this memory crisis, not by changing the math itself, but by restructuring the memory access, cleverly tiling the operation through the ultra-fast SRAM on the GPU. We're also seeing linear attention, reorganizing the exact same math to save compute, and rotary embeddings, or rope, injecting positional data directly into the dot product by actually rotating the vectors in space. The core operation survives. It just keeps getting clever.
So I really want to leave you with a permanent mental model today. The dot product answers one fundamental question. How much do these two things agree, and how strongly? When a neuron fires, it's asking, does this input agree with my stored pattern? When attention computes a score, it's asking, does this query agree with this key? Everything else we've talked about, the scaling, the normalization, the softmax, is just engineering to make that single question computationally well-behaved. The next time you look at a transformer architecture, I want you to see it not as some magic black box, but as billions of perfectly organized dot products, continually asking and answering this exact question. But it does leave you wondering, if the entire AI revolution is built on this single, simple operation, what happens when we finally invent an operation that's better?